So I figured it's probably a pretty good time to get started with some of these things, talking about some of our details today. So today might be the most important lecture of the entire semester, because today is the day that we talk about vectors. And vectors are an all-important thing. They are not just important arrows, they are very important arrows, and very important arrows to the point that I'm going to underline very and important. Right? Quadruply important arrows. They are going to be something that we're going to use for everything else that we are going to be doing for the rest of this semester, and everything that we're going to be doing next semester. Vectors show up constantly. They are like the physicist's greatest tool. Typically, we are going to see them like what we see right up here in the top left corner. Right? A little arrow, some sort of drawing. It has a length and a direction to it. We might also see big vector fields that you make up of different things. Right? And that's a whole bunch of vectors all put together in some different way, but all of them, you can kind of see if you zoom in, are built up of the same arrows in every single place. But before we dive too far into this description, we do have one problem that we started talking about last time, or I mentioned last time, but we didn't have quite enough time to solve through it. So I would like to start with this today, because if you have not finished the homework from Friday's lecture quite yet, then doing this problem might give you a good start on one of the more difficult parts of that homework set. So what we have is a rubber ball is shot straight up from the ground with a speed v0, or we can call that VA if you would like. Simultaneously, a second rubber ball at height h directly above the first ball is dropped from rest, no initial velocity. At what height above the ground do the balls collide? You only have variable names. You don't have any numbers associated with this one, so you're going to get an expression at the end of the day for this. And there's also a picture here if you would like some help with how you should draw this picture. Here's a pretty good picture, I think. A not bad way to describe that thing. But I want you to take the first 5, maybe even up to 6 minutes of this lecture and work on this one a little bit. See what you can come up with. And then after that, we will all look together to see if we got the right expression or not. And maybe some different ways to solve this one out if you chose a different path. So 5 or 6 minutes, we'll come back, check what you got. Okay, so let's start talking about this thing. So I want to draw this thing out. I know in the picture it's labeled A and B, and I'm going to continue doing that, but I love to color code these things just to make this a little bit, I think, easier to keep track of, especially when I have a bunch of equations running between different things. So what I'm going to do is first we talk about the green ball, and the green ball is going to have a velocity, call it v of b. V of b is 0. Starts from rest. Not going anywhere. But it does start at some height y of b as h, right? We said that's our initial height. And what I'm trying to do here is I'm trying to make sense of all of this stuff. I'm given a v0, I'm given an h, I'm given all these different things. And it's a little bit hard to keep track of all of it together sometimes. So I'm going to come up with some sort of naming scheme that makes sense for the picture and the scenario that I've got in front of me. So at the same time, I also know that the red ball on the bottom is going to start with some non-zero velocity, right? Call it v of a. And v of a is what they have given in the problem as v0. But VA makes sense because this is a and that's b. My initial height for a is 0. It starts on the ground. So for each of these, it's the symbol for not, and it's not as in N-A-U-G-H-T, 4 letters in place of the 1 that we could have, but that's English for you. So, yes, but it is typically just a no or a 0 or something like that. So we've got all these variables, and these are the specific cases for each of these. And then what I'm going to do is I'm going to draw a second scenario, right? We know at some point they collide. So there was step 1. Here is step 2, where they have collided in some fashion or another, and that actually looks like a collision this time. Excellent. Last section, that did not go so well. There was a little bit of a gap between them. But let's think about what happens here. So we know that they collide, and that means that this spot right here is y of f. So, and I know the balls have like some height to them and everything else, and that shifts everything up and down just a little bit. But for the most part, we're not going to worry about that. We're just going to say the distances here versus the size of the ball, it's not a huge difference. It doesn't matter. Say they collide at the exact same spot, y of f. That'll make this whole thing a little bit easier. Okay, so now we've got some of these things laid out, and what I'm also going to do is I'm going to give myself a variable bank so that I can talk about these things with a little bit more ease and really keep track of what I know and what I don't know, because in problems where I'm only dealing with things purely symbolically, it's a little bit harder to tell when I have the variables and when I don't if I don't organize them somewhere. So what I'll say is I have v of a, well that's v naught technically, I will have v of b is just 0. I'll have y of a is also 0. And I'll have y of b as h. I have one more thing that I haven't listed so far in this picture. What else do I have? Acceleration. And acceleration for each of these is negative g. So I'm not going to specify a or b, I'm just going to say acceleration is negative g because that's true for each of these. Now, I need to find this y of f. So here's what I'm going to do. I'm going to try and write out each of these things, and I'm going to see how much information I can get on each of these, and if any of these are solvable, and I'll work from there. So my different kinematic equations might work. Let me start with ball A, the red ball on the bottom. What I can say is y of f might equal the initial place where it was, which I know is 0, plus the initial velocity times however much time it takes to get there, minus 1/2 gt squared, right? That's my acceleration. Acceleration is a negative g, so that's where this minus is going to come from. Okay, I don't know y of f. I'm looking for it. I don't know t. Two variables, not solvable. The 1/2 is part of the kinematic equation. So that one didn't work. Let me look at the bottom one, because typically if I don't have anything on the top one, like that middle one for velocities, I'm interested in position, right, in some way or another. So then let me say, all right, well, let's take the final velocity of ball A, so that's v final of A squared, would be equal to my initial squared minus 2g, and the delta y here, final minus initial. Y final minus 0. Okay, I don't know this. I don't know this. And if I look between these two equations, there are 3 unknowns. Okay, well that's not working. So maybe this isn't enough information. Let's go over to the green ball. Let's see what equations we can come up with for that one. We might say for the green ball, it would end up at y final would be equal to the initial placement of this thing, which I know to be h, plus the initial velocity times t, which I know to be 0, minus 1/2 gt squared. I don't know y final, and I still don't know t, so that's not solvable. Okay, what about, let me do the same thing for this one. Let me say, all right, what about this? Kind of as my last attempt here at an equation that I can just come outright and solve. Final minus initial, y final minus the initial height. I don't know this velocity, I don't know y final. None of these are solvable. But maybe that makes sense. Because realistically, either one of these, they're kind of independent from each other, right? What they're doing, they're going to collide at some point, they're going to interact at some point, but until that time, when I drop the top green ball, what does it do? Nothing, right? It's just going to fall on its own, and it's going to continue picking up speed and changing its position. The red ball on bottom, when I launch it up into the air, it's going to launch up and then eventually want to fall back down, but neither of these really care about the other. It's only when they collide that they actually have some sort of meaningful impact. So I probably need to do something where I combine the two. What about the final velocities? Maybe that's a place to look. Does the final velocity of the red ball have anything to do with the final velocity of the green ball? Is there some way to relate those? That is an idea indeed, because what we can look at this and we can say, okay, well, the final velocities, again, they don't care about each other until they collide. And again, once the collision happens, this is one of those scenarios, I think I talked about this a little bit last time. When you have a collision, everything goes haywire, right? Everything that we're learning about kinematics is assuming that there are not collisions. Because as soon as you have collisions, there's a lot of details that come into play very quickly. It's a much more complicated picture, and one that we're not quite ready to talk about yet. We will eventually, but not yet. So we want to look either at the instant of collisions or right before them. But again, the final velocities have nothing to do with each other. What if I raised up h so that it's 1,000 meters high or something else like that, right? Then the final velocity of the green ball would be very, very fast, right? Exceedingly fast. But the red ball, maybe I just launch it up and maybe it hits at the top of the arch. And if it hits the top of the arch, then the red ball's velocity is 0, but the green ball is like storming down at that point. Like it just doesn't, there's no relationship between those two. There's nothing I can do with these bottom equations to make them look at each other in any sort of way that's compatible. So instead, we take that idea of, well, there's more to a collision than just being in the same place. If you're walking behind somebody on the sidewalk, at some point in time, you will be in the same place that they were, right? If you're walking 5 seconds behind somebody on the sidewalk, then in 5 seconds' time, you will have shared that spatial coordinate with them. But the time is different. You don't run into anybody unless you're trying to be at the same place at the same time. So this collision is not just sharing a coordinate in space, it's sharing a coordinate in time. And that is the key point. That means that looking between these two equations, the red t and the green t are exactly the same quantity. Now I have two equations that share two unknowns. This is a solvable system. So I was criticized last semester for how last section for how I solved this problem. I did it in a substitution manner. And it came out a little bit more complicated than I would have normally liked. So what I'm going to do in this case, I'm going to say, hey, this is y of f is equal to this stuff. This is y of f is equal to this stuff. No, both of these should be negative because both are going to be experiencing the pull from gravity towards the ground. G goes this way for that. Well, I shouldn't do it like that. I said G is pulling me towards the ground for this one. G is pulling me towards the ground for this one. There's, something launches ball A up, but gravity's still pulling down on it. Directions of velocity and acceleration can be independent. If acceleration is in the opposite direction of velocity, that means that the speed is going down. That's the difference on those, right? Because if you're driving a car or something else and you hit the brakes, what you're doing is your velocity is still going forward, but your acceleration is pulling back. So what I'm going to do here is I'm going to say y of f is equal to y of f. Can we agree on this one? Hopefully. I'm going to take the red y of f and say this is v(a)t minus 1/2 gt squared is equal to h minus 1/2 gt squared. Yeah, this is this is a much easier way to do this than substitution. I would recommend doing this one. This is the easier way to do this, absolutely. So what I can do is I can cross out, there's a minus 1/2 gt squared on each side. That doesn't matter. So what I'm left with is that time, one of my unknown variables, must be equal to h divided by v of a. H is something that I have. V of a, v naught, I have that. I can successfully now write into my given variable box that t is equal to h over v of a. So if I ever need that, I have it. If I see t in any equation, and we are about to see t in an equation, we know that that is a variable that we have at this point. It is one of our tools to use. So what I will do now is I can go to either one of these. Which one looks easier? I guess I'll take the green equation. Not that it matters at this point. Question, though. Sure. So the YF versus YF, this is another way to solve out systems of equations. What I'm basically saying is that if I look at my red equation right here, its y of f is equal to all of this stuff, right? The quantity, whatever y of f actually is equal to the rest of this expression. It also happens to be that y of f in the green equation, y of f by itself must be equal to this expression. So I'm kind of doing my commutation here to say, well, if y of f is equal to y of f, then the red y of f better equal the green y of f. Does that make sense? Absolutely. So the other way to do this, if you're not entirely sure, you can go through with this thing. You could do a substitution, but from last time when I did something like that, where did I put that? The substitution ended up being a little bit, where did I go with this? The substitution ended up being nasty. There were a lot of steps, and none of them were very pretty. So let's take it from past experience. The easier way to do it is to set the two equations equal to each other in this case. But a substitution will get you there in exactly the same way, right? It's just the math is a little bit nastier. But I can go with the green equation and I can say, okay, well, y of f h is a given, minus 1/2 gt squared. But now I'm going to replace that with this right here. That's my expression, and that's it. As far as I'm concerned, h given 1/2 g h squared over va squared. I've got it. That's everything I need. All in variables that we have. So, and again, this is kind of similar. Some of the conditions are set on this problem are the same as in one of your homework problems. Right? The same thing is true when the two balls collide. Regardless of where they collide, they share the same position and the same time. Now, in that homework problem, there are some details that are a little bit different, though. So it's not just the same answer. Yeah, I could plug it into either the red equation or the green equation, and technically speaking, it should give me the answer, the same answer either way. And it would just, you would have to do a little bit of algebra to make those two look similar. It's not necessarily that it's things that are crossing out. I've crossed out the one in the green equation because the y of b is h. For the people asking v0 or va, it's the same. That's partially done on purpose because you can easily kind of confuse which one it is. But yeah, it's looking for, I like to do this as my problem-solving thing if I really don't know where to start from it, right? In a case like this, I'm not entirely sure which equation is going to lead me to the final answer of this thing. What I'll do is I'll start writing out some of these equations, and I'll highlight the things that I don't know. And if I can find a system or enough equations that share variables that I don't know that I can solve it, then I'm golden. But that's part of why I like to highlight these things, because now I know from my top red equation, I don't have yf, I don't have t. From my bottom red equation, I don't have the final velocity either. But since that final velocity doesn't show up anywhere, I can't really do a lot with it. But these other variables that do show up in multiple places like t, I can do something with those. Yeah, they share the same location at the same time. Absolutely. So, I'm going to say, let's go ahead and start taking a look at some of our vector nonsense, right? Because we do have some of that stuff, our good stuff that we need to talk about today. Let me try and zoom out to the right thing. So, all of these things that I keep talking about, this acceleration, this velocity, this position, I mentioned this before, but these are all what we call vector quantities. And a vector quantity is any sort of variable that has both a magnitude and a direction, right? And last time I kind of wrote it on the slides and I hand waved my way around it, but I didn't really nail down a specific definition for it at the time because, well, we were kind of saving it to talk about now, right? Now we really need to start to think about these things in a little bit more depth. But you probably have already seen a lot of these vectors, right? Position, velocity, acceleration, force. When we talk about force will be another example. But there's also momentum, torque, magnetic field, angular velocity, area, electric field, path, dipole moments, the pointing vector, all sorts of nonsense. There are many, many, many examples of vectors. They are an extremely useful tool. It combines direction and magnitude into one single quantity so that we can talk about it. There's a lot of specific operations that go on exclusively with vectors that dealing with scalars just, it doesn't do quite the same thing. That being said, scalars, if you haven't heard of this before, scalars are a very fancy way to say numbers, right? Scalars are a quantity only. Nothing associated with any sort of direction or anything else. So some examples would be mass, temperature, energy. Time is another example here. Time does not have a direction. Not for us, not right now. If anybody has looked into relativity or anything else, that maybe sounds a little bit strange. But for us, time is going to be one of those quantities that is not a vector. Right now, at least. One day we will talk about breaking all of this stuff down and ruining all of this good classical physics that we've got. So you might notice every single one of these vectors I've drawn out has this fancy little hat, right? It's another little arrow. That little arrow says, hey, I'm a vector. So for example, if we have our velocity vector right here, if we were to take away the hat, that is talking about the magnitude only, the number only. We have removed the direction. So what is v without the fancy hat? What does that symbolize? Any guesses? Speed. Yeah. Right? Speed is just how fast you're going. It doesn't care about the direction. So if we see v with a hat, that says, hey, this is velocity. If we see v without a hat, that says, hey, this is speed. Does that make sense? Okay. Perhaps silence is the best response to that one. Why is torque? So torque, it's not an R. There's a little bit of a tail on the R. Torque is technically the Greek letter tau. Torque is a vector, but we'll talk about that in good time. Torque is a strange vector. We'll talk about that one at good time, though, when we get to rotational motion a little bit more. So, vectors, big deals, right? Every single one of these, important to keep track of. Sometimes, if you want to talk about this, so I'm talking about some of these things, like I could take away the hat from the vector, and then it would just be the magnitude. The other way to do that, if you want to be explicit, if you want to make sure that everyone knows you are talking about a magnitude, a length, and not the vector, what you could do is you could add the hat and then put absolute value signs around it. That way, nobody thinks that you just forgot to put the little arrow over top or something like that. This expression right here says, I am absolutely looking at a length and not a direction. And I'll have that on a slide in the future as well. I'll bring that point up again in just a little bit. But drawing vectors is about to become one of your favorite activities, whether or not it already is, and I have to assume that you've already enjoyed it so far. But drawing these things out, making good pictures for all of these things is imperative to doing well in physics. And I mean that. I don't just say that for my health and everything else. I mean drawing pictures is good. I draw pictures for all of my problems, not just because it makes it more clear for you guys, but because it makes it more clear for me too. So drawing these things out properly is a pretty important step. Whenever we're going to draw these things, I'm always going to draw them like an arrow, similar like this. So if I have an A vector, then I'm going to start from some point, I'm going to end at some point, and the arrow part goes in the direction of where the final position is, right? So if we have an S vector, for example, S vector, just like this, has some initial, some final. The arrow goes towards final. One of the other things that we do with this is that we try to label some sort of direction with it as well. So most of the time we will see theta or phi or 30 degrees or something like that to specify what direction is it going relative to our normal axes, x, y, z, whatever we want to have with all of those things. So and again, if I want to talk about only the magnitude, only the length of the vector, not the direction, then I have two different ways to do that. I can either take off the hat or I can dress it up in a coat as well so it looks really fancy. It just says magnitude of. I can move myself over to the, oh geez, I have my microphone right in the way of some of my symbols. Top left capture denotes the magnitude of the vector and is a non-negative. That is to say, speed is always positive, right? Speed is always a positive quantity, or zero, I should say. So magnitude, in a similar manner, is always 0 or greater than 0. It's never negative. So we like to name these vectors. We like to tell us what the direction is. And then if we want to describe these things, we could say 30 degrees above the positive x-axis, or we could say 30 degrees counterclockwise from the positive x-axis, or there's a number of different ways that we can talk about these things. We could say 25 degrees north from west. Then we'd start at west and we'd go 25 degrees towards north, right? There's a variety of different ways that we can describe this direction. And none of them, well, some of them are wrong if you put the wrong number or something else like that. But if you have a different way of describing what direction your vector is pointing, that's okay. We might have different descriptions for our vectors. The important point is that we can compare our pictures, compare our descriptions, and we can agree that we're trying to say the same thing. Maybe we're saying it in a little different way, right? We're using different words, but we're trying to mean the exact same thing, and that's okay, right? I am not super worried. I know if you've been doing a lot of math, oftentimes we like to focus in on always doing things relative to the unit circle, so always counterclockwise from the positive x-axis, but I'm not going to be that picky. I'm a physicist. I'm not that picky. That is my stereotypical impression of physicists. We're usually not that picky. So, here are some varieties of ways that we can start to do things with vectors, right? Vectors on their own. Neat. Adding vectors, an important point. If I have two vectors, A and B, then we could graphically add these together by taking A, taking the head of A, attaching the tail of B, and then going from the tail of A to the head of B, kind of like this, right? We stack them together, and if we have more to add, then we just keep stacking them on in sequence. A plus B plus C plus D plus E, stack them all together in exactly the same way, from the beginning all the way to the end, draw a line, that's your resulting vector. If we wanted to subtract, that's not really any different. All we would do instead is we would say, okay, A minus B, that's kind of like A plus negative B. Negative B just points in the opposite direction, right? I'm just flipping the direction of the vector. The length would stay the same, the direction would flip. So it would look something like this instead. There's nothing I'm covering up in the bottom right corner. This is all it is. It's just white space over there. So that's an important thing, right? Vectors are a little bit complicated because there's some different things going on in some of these different spots, like multiplication is a little bit different with vectors. But we'll get into that in good time. For now, concept check, real fast. I've got two vectors, A and B. If I were to add these two vectors, what would the result look like? Take 30 seconds. You're welcome to draw this out if you'd like to. But what are we thinking? Ooh, we've got a little bit of variety in here. Not too much, but a little bit. I think I would agree with C. If I really wanted to do this graphically, then I could just say, okay, well, I'm going to take A, and then I'm going to attach B to where A ended, and that's where I'd end up. Here's my vector C, call it. Right? What would happen if I did b plus a? Would I ruin everything? Would it be different? Would it be the same? What do we think? Yeah, probably the same, right? I mean, let's draw this real fast. What if I started with B? If I started with B, then I'd go down here first, and then I would go up here, and yeah, it ends at the same space, right? Which is a nice thing. This is actually a feature that you're probably very used to seeing. 2 plus 3 is the same as 3 plus 2. That will not always be the case for vectors. Vectors have some weird things that it doesn't commute. And I know that sounds very alien right now, but eventually, one day, we will get to those descriptions. But right now, for vector addition, it works just fine. A plus B is the exact same thing as saying B plus A. So I would have had, this would have been A, this would have been B, then this would have also been B, and this would have been A. But what we do is we said, okay, we started at this point. Here's my initial point. Here's my final point. Yeah, and I always draw I would add all of the vectors that I would have up together. If I wanted to do, for example, let's do A plus 2 times B, or A plus B plus B. I'd have A plus B plus B. Then my vector would look like this instead. I would still take my initial to my final. This is A plus 2B. Fantastic. But yeah. The new tail goes to the old tip, and then you just keep stacking those things on until you have finished whatever process you've got. So, but I bring this up, that A plus B is the same as saying B plus A, because as we're going to start looking here, let me draw on those points myself. Somehow I missed those when I was erasing things earlier. If we have a vector A, there are parts of A that might go into X and Y, right? If this thing is anything like what we have seen all of these other vectors be, most of these vectors are not pointing along the X or the Y axis, right? And that's complicated. Because, I mean, sure, that's fine, but like everything that we've seen so far, one-dimensional motion, over kinematic equations, those have all typically dealt with one-dimensional things. And you have to assume that I'm not just going to teach you things that are immediately going to be outdated and useless, that they would still have some use somewhere, somehow. But as it turns out, vectors, if they are going in any other direction than just along X or Y, we can split these things up into what we call vector components. That is to say, this vector A that I have right here has essentially a portion of itself in the X direction, call that A of X, and a portion of itself in the Y direction, call that A of Y. Now for these two portions, can we agree, exactly as I have drawn it, that A of X, the vector, plus A of Y, the vector, added together form my original vector A? That looks all good to me. And what if I went in the opposite direction? If I had started with A of Y, and then I went to A of X, yes, it points to the same vector. It doesn't matter what order I add these things in. If I take the individual components, add them together, I should get my original vector back out. So then the question is, what is this extra stuff? What is this I hat and this J hat? And I'm calling them I hat and J hat. So I know I've been saying fancy hats for the vector signs, but these are even fancier hats. These are very, very important hats, and not many things can wear them. Anything you see wearing this very fancy hat is what we will call a unit vector. And unit vectors are kind of like the opposite of magnitude. Unit vectors are trying to specify a direction. So for a lot of these things, for example, if we were to write out some sort of regular kinematic equation, right? Let's be real here for a second, and let's say X, come on now, I'm trying to make a point, help me out. Let's say X vector is equal to the initial X vector plus the velocity vector plus 1/2 a t squared, but acceleration is also a vector. When we look at these things, now they're vectors instead of just being numbers, but we can all agree it means the same thing, right? It's a place, it's a direction, it's got some of that stuff associated with it. So X would be measured in meters. Velocity measured in meters per second. Acceleration measured in meters per second squared. Unit vectors are unique in that they do not have a unit associated with them. Even angles have a unit, right? Angles either come in degrees or radians, and that is technically a unit. But that is not true for the unit vectors. And the reason that's not true for the unit vectors is because the unit vector's only job is to tell you about a direction. So when we look down at this expression, this is saying exactly the same thing as the vector a of x plus the vector a of y, but now we are using the quantity a of x and the quantity a of y. I hat, j hat are telling us about the directions. So anything that is very useful, you might find this true in life, anything that is very useful will probably have a lot of different ways to talk about them. And that is true for cases like this. We might talk about the individual component vectors. We might talk about the components and then multiplying that with a direction to get back out our vectors. There's a lot of different pieces that might flow into these things, but there's a reason, and it's that there are different places that this language is most useful to use. We've got to get a little bit of practice with this because I have to imagine that this is not a very common thing. If I hat and j hat is a little bit confusing, I am more than happy if you decide to use instead x hat and y hat. That means the same thing to me. That little carrot top hat implies a unit vector. So if you want to do x hat, y hat, and z hat, that is equivalent to I hat, j hat, and then k hat when we eventually get to 3 dimensions. So I am not upset if you want to use either one of these sets. Totally fine by me. I know it's a little bit confusing to immediately jump into I hat, j hat, and k hat. It's strange. And if you are an old physics or math textbook from the 70s, you're cruel enough that you instead use the unit vectors I1, I2, and I3. And that's disgusting, and we're not going to do that. But if you're ever looking through an old textbook and you see stuff like that, that's what it means. They're trying to do the same thing here, but they just don't care about clarity. So let's try this out real fast. If we see this vector c right here on some sort of graph, what are the x and y components of vector c? Take 30 or so seconds, look at it, maybe measure it out if you would like to, and see what we get. Okay, I see a fair amount of D, and I think I would agree with that. Let's measure it. Let's try it real fast. We want to find what the x component is. I'm going to start from the tail of this thing and go towards the tip. So I move over 1, 2, 3, 4 to the left. -4. We kind of already know which one this is, right? There's really only one answer. But let's confirm it just the rest of the way. Then we're supposed to go up by 2. D is indeed the correct answer. So you might question, you might look at a lot of these things that we've seen so far and say, hey, do we always have to start from the origin? And no, we don't. A lot of the time we will, but we don't have to start from the origin every single time. Vectors can be anywhere, technically. It's just much of the time we will see them from the origin or from something in the middle. When we talk about forces, for example, we'll put our object in the middle. We'll put a block right there, and then we'll draw all the forces acting on that thing in the different directions they'll be going. So, if you have this thing graphically like this, and you have these tick marks, and you can read exactly what the vector components are supposed to be, that's nice. It's not super common, though. A lot of the time, we're going to be in a little bit more of a rough position than that. We've got to do a little bit more calculation. So, sometimes if you would like to know what these vector components are, and you have the total length of the vector, and you have something that indicates a direction, then what we're going to have to do is we're going to have to draw some good old triangles. If you're used to working with unit circles, I would ask you to focus on triangles instead. Always check the triangle, because I'm saying it down here. Don't assume that x will always be cosine. Don't assume that y will always be sine. Often, that's true, but it's not always the case. And if you always assume that x means cosine, you're going to be in some sticky situations in the future. But if that is true, for example, in both of these problems, that would be true, then what we could say is that if we have this angle theta right here, then the x component would just be this side of the triangle, right? This is a of x, this is a of y. A times cosine of theta, and a times sine of theta. If we remember our good old friend SOHCAHTOA, and if you have not heard of SOHCAHTOA, this is a wonderful thing to have. It is my second favorite type of TOA. So this would say that sine of theta, for example, would be equal to the ratio of the opposite leg over the hypotenuse. Ka is cosine. I have not given myself enough space to write this out properly. Let me try. Let me space these out a little bit better. Give myself a little bit more room so we don't get like layering these writings. Cosine of theta, and I'm writing out the full name, would be the adjacent over the hypotenuse. And finally, TOA means that tangent goes as the opposite over the adjacent. So anytime I'm drawing out my triangles, if I have a big triangle like this, here's my angle theta, this is the opposite side, this is the adjacent side, and the hypotenuse is the hypotenuse of the triangle. If you have not seen SOHCAHTOA before, there you are. It's a really easy way to remember that. For some reason, way back in early high school, I had a geometry teacher say, don't memorize SOHCAHTOA because you won't always be able to use that. And this is my 8th year of doing physics, and I still use it, I guess. So if you have ever heard of something similar, it's still useful. It's still nice to have. It's a quick little thing that you can say to remind yourself of the order of these things in case you ever forget. So one of the last things I do have here, though, highlighted in purple here at the bottom, is imagine what would happen if the angle went to 0. I love to do this to check to make sure that what I have assigned cosine and sine is correct. What is cosine of 0? 1. What's sine of 0? 0. Yeah. For those things, imagine this vector right here, A. What if theta went to 0? If theta went to 0, then A cosine of theta is just the whole length of A, and A sine of theta would be 0. If theta went to 0, A would be pointing in the x direction. That answer makes sense. That's cohesive to me. So I like to do this. I like to imagine what happens if the angle goes to 0, because if the angle goes to 0, does it point in the direction I expect it to, right? The one that it points in now should be the cosine, and if it's not, I need to look at this, and I need to be a little bit more careful with my triangle, and I need to not just be using the unit circle. So, let's try this out. Get a little bit of experience with it. I have 3 different vectors. I have given you the total length of the vector and some sort of description as to what direction it should be going in. Your task for the next 4 or 5 minutes is going to be to take each of these 3 vectors, draw it out on some sort of coordinate system. You don't have to draw any sort of real length. That's fine, right? These are all relative lengths anyways. I'm much more interested in making sure you get this thing in the correct direction, labeling the angle, and doing some good stuff with drawing these things out, getting used to that. Take all 3, draw them out, find the components, come back together in 4 or 5 minutes, see what you got. So I would say, let's go ahead and start taking a look here. And I gotta move this to the side or I'm gonna mess up these numbers, as you know I already do. But what we're gonna have here, I'm probably gonna just draw all 3 of these on their own separate ones, but maybe the last 2, we got some good space for it. That's not very even at all, is it? Try something like that. Perfect. So now we know that our first vector r is 100 meters long in total, 45 degrees below the positive x-axis. So that is to say, if we here below positive x-axis, we start at positive x-axis, somewhere over here, and then we say below that 45 degrees. Bam, something just like that. And again, it doesn't have to be exact. I'm not worried about a length. You don't need to put any sort of markers here to indicate exactly what it is, unless you are doing a more graphically intensive problem. For the most part, I just want to see a picture, right? We're just trying to get a picture to help organize our ideas. So this is my vector r. We know that this angle right here is 45 degrees. So if I wanted to find the two components of this, what I would do is I would say, okay, I want to make a triangle out of this thing. I have this angle 45 degrees, so let me put that inside of my triangle. Something like that. Then this piece is r of x, and this piece is r of y. And I can make those vectors if I would like to, either way. But what I can do now is I can say, okay, well, then each of these components would be r of x is equal to, if I look at this side, I say, hey, my angle right here, this is adjacent. This is opposite. So following my classic SOHCAHTOA kind of rules, I could say, well, then r of x would be equal to cosine, r times cosine of 45. R times cosine of 45 should give me something like, I think, 70.71. Correct? 70.71, and then I am going to specify meters because we were told that there was a unit associated with this vector. Now doing the same thing with r of y. Now I've got a little trick to this. If mathematicians are very, very exact and everything else, they might get a little bit upset with this answer. But what I'm going to do is I'm going to say, hey, I know what direction this thing should be going. I see a 45-degree angle, and I see r of y is going downwards. I'm going to say this is negative r sine of 45. Because 45 degrees, sine of 45 degrees is a positive quantity, right? To make it a negative quantity, I slap a negative sign on the front and say, I know what direction this thing should be going. I see a triangle, I know what direction it should be going relative to positive and negative, so I'm just going to slap a negative sign on it and call it a day. That means that this answer right here would be negative 70.71 meters. So I could take this one more step. Why is it cosine r cosine of 45? That would be the side length of this triangle. If this length is r, right, and that's the length of the vector. So I did see one good comment that I saw in one of the chats here was that is the number value of these vectors always the hypotenuse? Yes, that's a fantastic way to think about these. The total length of a vector is always the hypotenuse. In the case that it is not a triangle, then that's just the line, essentially. Right? One of the first math jokes I ever heard was, what do you call a triangle with side length 0? Collapsed. Now that you've taken a break from laughing, it works out just as well. But that's why it's r cosine of 45 degrees, because it's finding that side length r of x. One of the ways that we could write this out, though, if we wanted to be fancy with it, and we wanted to write this in what I would call component form, then what I could say is that my vector r, instead of writing it out 100 meters long, 45 degrees below, yada, 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 what I could instead say is that r is equal to 70.71 I hat minus 70.71 j hat meters. That's a fancy way to write this thing. Instead of dealing with the x component and the y component, I can put it all together in one nice clean line. Okay. But how are we feeling on this one? If we're feeling all right on this one, then I think we'll be all set on the others. So I'm testing the water now. That is coming, if I'm following my SOHCAHTOA kind of rules here for the triangle, it is the circumstance in this problem that r of y is the opposite side length. So that's the one that gets the so out of SOHCAHTOA. Sine is equal to hypotenuse of opposite over hypotenuse. So multiply over the hypotenuse. Hypotenuse times sine of theta gives me the opposite side length, r of y. Does that make sense? Okay. Hopefully, for some people, I remember myself was absolutely included in this. We need to shake off some of the geometry cobwebs. But, being in radians. If you really love radians, you're more than welcome to keep working in those things, but you're going to have to do a lot of degree to radian conversions. So, let's take a look at another one. Draw our axes real fast, draw them very badly because my hands are shaky, because there is a consequence to drinking this much coffee. Now we have our velocity vector v, 300 meters per second, 20 degrees above the positive x-axis. So we say above positive x-axis, start at the positive x-axis, go 20 degrees up from that. Do this one in blue to specify it a little bit. Everything is at a slight angle, which is fantastic as always. That makes it very clear. But that's my vector right there, and then I will specify that, hey, we said this is 20 degrees. Right there. So now looking at my components for this thing, I make a triangle. If I'm looking at my triangle, then I could say that this piece right here, that's total length v, 300 meters per second. This down here is v of x, because it's going along the x direction. This right here is v of y, because it's going along the y direction. I have, as part of my triangle, let's do this in a light gray, my hypotenuse up top, my opposite leg from the angle, and my adjacent leg to the angle. So between the three of those, I can take my classic SOHCAHTOA kind of approach, and I can say, all right, well then v of x, being the adjacent side, would get the cosine. Plug that in. V is equal to 300. What I should find at the end of the day is 281 meters per second. Or I guess 282 if I actually round that properly, isn't it? 282 meters per second. That's what I have for the x component. For the y component, I could say that this is going to be, I might as well just plug this in, 300. Sine of 20 degrees, and I have left both of these positive because based on my picture, I can see that I have positive x and positive y. So I'm not slapping a negative sign anywhere unnecessarily. What I should end up with at the end of the day is 102 meters per second in the y direction. Similar thing, I could combine these all together into a component notation, and I could say this is 282 I hat plus 102 j hat meters per second. R being the hypotenuse that we were given, R would have been equal to 100 meters. Absolutely. And for our last one, I'm not even going to draw a new picture because it's kind of out of the way. What we have for the last one is acceleration is 5 meters per second squared in the negative y direction. That one's nice and easy. Negative y direction. And I know that's a little bit hard to see. There's our green arrow. That is our acceleration. I could write that out. Negative 5 j hat meters per second squared. That's all there is to that one. We love those vectors that are already pointing along one of the axes. It's just so much easier to deal with. So, let's keep moving right along. What if you didn't have the hypotenuse and angle? What if instead you were given the components? Well, that'll work just fine, right? There's no reason to be scared of that or anything else. We can take these processes in exactly the opposite direction because, again, it's just triangles. And I can move myself before somebody says it to right up here so you can read that bottom thing. if you already have the components, then you have the side lengths of the triangle. Finding the hypotenuse is the Pythagorean theorem, right? Nothing crazy on that one. Ax squared plus ay squared, take the square root of that whole thing, you get the magnitude of your vector. If I wanted the direction, this is one that might be a little bit more careful. For the most part, though, what we can always do is we can take an inverse tangent of these two components, right? Following our TOA part, the best part, tangent is equal to the ratio of opposite over adjacent. That is to say, if I take the inverse of each side, inverse of tangent of theta gives me just theta. Inverse of opposite over adjacent is something your calculator does. Here is my super jank calculator, right? It's lovely. You can see the massive black hole in the screen. Both of the ports are completely destroyed. It's a rescue. It's not a very healthy rescue, but it's a rescue. And it's also completely dead right now, so I can't actually calculate anything on it. But if you have one such thing and you have not seen any sort of any of the inverted things like that, what you might notice, sine, cosine, tangent, the little things above them, the second functions above those, where it says sine to the negative first, cosine to the negative first, tangent to the negative first, that is exactly what we are going to do for these. Technically speaking, again, if there are any mathematicians in here, they're going to be very angry because they would be like, well, that's supposed to actually be arctangent, and inverse tangent is something completely different, and I know it is, but everybody else does this already. So if you hear me say arctangent or inverse tangent, they mean exactly the same thing. Arctangent is just the actual one. Inverse tangent is what we popularly say for some reason. I don't know what it is. But anyways, we might run into some issues because realistically here, when I plug in a of y and a of x, for every single one of these things, there are two potential answers. And your calculator is going to pick one of them. And it might not pick the one you actually want. And that's not good. Because realistically, what can happen here is we have to imagine, let me switch myself back over to here so I can draw some stuff here. Let me draw some axes real fast. If I have something like this, and I had some sort of arrow going from the origin like this, some sort of triangle perhaps, could we say that for this angle theta right here, that tangent of theta would be equal to opposite over adjacent, right? This is like exactly what tangent means, opposite over adjacent. We can all agree on this one, correct? That's what we have classically seen our trig functions to be the entire time. So what would happen if we put a negative sign in one of those? What if we put a negative sign in two of those? What if instead of drawing this one, let me do this one in blue now, what if instead I had gone like this and said, let me do this instead, and let me call this one phi. But the components here look kind of the same in a lot of ways, right? I still have this kind of weird, it's a symmetry pattern to it, right? But now my opposite and adjacent are both negative quantities, at least on my graph like this. Negative over negative, that's a positive number, right? This is a little bit of a weird example because this is the case where we had two different positives, but we might end up with some different vectors that point like this. The problem is your calculator is going to come up with one answer, unless you've got a very smart calculator and it gives you two. But this thing that I have in my hand, I don't have high expectations. I imagine that most of your calculators are going to be in similar scenarios. So this green vector right here, as nice as it would be, our calculator cannot tell the difference between that green vector and this orange vector. right? It thinks they're the same picture. It does not know which one to pick. So what we have to do is we have to be smarter than the calculator, which sounds like a trivial task, but from personal experience, not to insult anyone here, from personal experience, it's not always as easy as it feels like it should be. What we are going to do instead is we are going to take away that autonomy of the calculator to actually pick one of these things. All calculators, if given positive numbers, love to spit out things in quadrant 1. It's just so easy for the calculator to do. It doesn't give you an answer in quadrant 3. It thinks that's stupid. So when we are left in quadrant 2 or quadrant 4, some calculators like to give answers greater than 90 degrees. Some calculators like to give answers of negative instead. And which one it is entirely based on what calculator you're using. Sometimes they have ways to change it, sometimes they don't. We're not going to bother. We're not going to bother. We are not going to inflict that upon ourselves. Instead, what we are going to do is we are going to say, take the closest angle, an axis that you pick, and make sure that that angle is less than 90 degrees. Make a triangle. No triangle has an angle greater than 90 degrees. Well, I mean, there are, but not a right triangle. We make a right triangle. We make sure that angle we're picking is less than 90 degrees. Everything works out better. We figure out which ones are positive and negative based on the picture that we see in front of us. That is to say, if we are trying to find this angle phi, then we are going to take the absolute value of the two components and piece it together afterwards. So, quick concept check. We have a vector, and I'm going to say that we are following the classic directions. Y goes that way, X goes this way. My vector A has a total length of 5 meters. Which of these 5 choices most accurately depicts what I have in my picture? Take 30 seconds, think about it, let's see what we come up with. All right, I'm only seeing a few handful of answers. I think we might be running out of steam at this point, but that's okay. What I've got right here, I'm first going to try and figure out, roughly speaking, what direction this might be going in. So I'm going to look at this thing and I'm going to say, okay, I see a negative x and a positive y. Going piece by piece. That's a positive x. That's out. Negative x, positive y. Maybe. Positive x, positive y. Nope. Negative x, positive y. Clears. And negatives, no. Now, why is it B and not D? What's the other part of this? We have the rough direction down. But what's the difference here? That is exactly it. The length really matters here. Sorry to interrupt. Pythagorean's theorem should tell us what the length of this thing should be. The components matter beyond just telling us the direction. This is a classic 3, 4, 5 triangle, which if you're not familiar, there are certain triangles that share special relationships. A 3, 4, 5 triangle means that one length is 3, one leg is 4, and the hypotenuse is 5. 3, 4, 5, the negative 4 plus 4 does not give us the correct total length of the vector. It gives us something else. So my negative 3 plus 4 puts us in exactly the right spot. So, now I've got a small little variety pack of different vectors for you here. All of these are written out in this same component form that I keep going on and on and on about, right? And there's a reason. I love these. We're going to keep using them. For each of these vectors, here's what I want you to do. Draw out your axes. Draw the vector. Find its direction. Find its magnitude. All 3 of those for each of these 4 vectors. So, take the next 4 or 5 minutes. closer to 5, say. And then we will take a look at this one all together. Okay, how's about we start taking a look at this thing? So I need to pull this off, or actually I have it written somewhere else. I don't need to pull that off. I can just jump straight to this one. So aside from our hodgepodge of random colors, what I'm going to do is, while we're here, let's just go ahead and draw all 4 of these. Here's part A, part B. None of these are particularly accurate for being purely vertical or horizontal. Excuse me for a minute. Talking like this is like teacher voice mode and everything else. Takes a little bit more out of my voice than just regular talking does, so a lot of it goes out pretty fast. But with as much coffee as I drink to maintain it, we run into issues with those shaky hands and actually getting things that are level or purely vertical in any way. But that's okay. So we're going to start our first one here with vector A in red. And vector A, we are told, is 4i hat minus 6j hat. So a little bit in the x and down in the y. Something like this, perhaps? That seems all right to me. It doesn't have to be exact. I'm not going to be measuring any of these pictures with a protractor or anything else because why would I, right? Again, most of the time, this is about helping organize our thoughts, which is not something that you should sneeze at. I mean, this is like an incredibly useful thing to have. So what I'm going to do, it is very common to draw all these things from the positive x-axis. So let's start with that. Let's call this angle right here theta. Then I want to make a triangle around that theta. So I'll put my x just like that and my y just like that. Let's go ahead and label those while we're at it. A of x, a of y, the full length of a. All of those things labeled on our nice pretty triangle at this point. So we want to now find direction and magnitude. I'm going to start with magnitude because it's probably the easier of the two. The magnitude a, using Pythagorean's theorem, is just going to be the square root of the x component squared plus the y component squared. Take the square root of that thing all put together and we end up with an answer of 7.21. And that's it for that one. So we have a magnitude now. Now let's find a direction. So we have our angle theta labeled here. What I'm going to do is I'm going to remove any possible agency from my calculator. Again, I do not trust my calculator. It is very good at doing calculations, but it's not very good at actually interpreting those calculations in meaningful ways. So what I will do is I will say theta is equal to inverse tangent or arctangent of the opposite side, this one, over the adjacent side, a of x. And I'm going to take the absolute value of each of these things to remove any such agency. So when I do that, my calculator spits out a number 56.3. Luckily for me, I do have a little bit more of a complex thinking process than my calculator does. And I can look at my picture and I can say, okay, well, I agree. Theta, whatever it is in quantity, is 56.3 degrees. Some people might like to call that negative 56.3. Right? And that would be from the unit circle interpretation. That would work for me. What I might also say, just to make sure that I'm being explicit, would be 56.3 degrees below positive x. That would mean the same thing to me right there. 56.3 degrees below positive x, that says start at positive x, go down 56.3 from that. So let's take a look at our next one. Let's draw out our vector, and we are given, in this case, let me make sure that I'm not colliding in the space that I'm going to be writing in. My vector r is now given as 50i hat plus 80j hat. between those two things, what I'm going to do is I'm going to say, okay, well, I'm a little bit in the X, I'm a little bit more in the Y. So there, that looks good, right? Relatively. Doesn't have to be perfect. I will label it to make sure we're all on the same page. I will keep going from the positive x-axis. That worked last time. Call that theta. Then I want to put that inside of a triangle. So I will draw out my x component. I will draw out my y component. Now I have a full triangle. And if I would like to, I can label this as r, r of y, and r of x. Now I have a nice pretty picture, and I have a theta labeled on this thing. So I'm going to find the magnitude. I'm going to start with Pythagorean's theorem. 50 squared plus 80 squared. Put those two things together, and I should end up with something like 94.3. And in this case, we actually did specify units. So this was 50 I hat plus 80 j hat meters. That means that our magnitude is 94.3 meters. My direction, theta. I don't need to take any agency away from my calculator because both of these quantities are already positive. But I am going to need to take the opposite over adjacent. So that is opposite over adjacent, ry over rx. 80 over 50. We should come out of this with an angle of 58.0 degrees on it. And I could say 58.0 degrees, and if you took a unit circle interpretation, that would be sufficient. That would be enough right there. I could also say that this is 58 degrees counterclockwise from positive x. That's another way, right? We could say above positive x, or we could say counterclockwise from positive x. For the Canvas quiz questions, sig figs is not a super important thing because there's a little bit of a bound on those things. So as long as you are most of the way there, if you had a slight rounding difference or anything else, you should be all set for those things. And it should say which whiteboard question is which over top of, like, with the questions. It starts with whiteboard 3-1B or whiteboard 3-2C or stuff like that. Question 3.1 was the... Shoot, not that one. This last one? This last one that we just looked at. So 3-1 was when we were finding the components. So that one was our vector r for 3-2. Let's keep going around in these things. Now we have a vector v that we are told v is equal to negative 20 I hat plus 40 j hat, units, meters per second. So between all of those things, what we could do, let's draw this thing out. And I'm going to get a little bit funky with this one. Let's show what a different case might look like. Let's draw right there. I'm going to make this look different. I'm going to say, what if instead of going from an x-axis, we went from the y-axis? That right there. How does that change? Well, let's find out. First, the magnitude will not be any different. Right? The magnitude, no matter how you do the magnitude, it works just fine. So I have v of x, and I have v of y. The magnitude, v, I'm just going to take the square root, and remember that when I'm squaring something, the negative sign goes away. Don't talk to me about imaginary numbers. 20 squared plus 40 squared, because 20 squared is equal to negative 20 squared. They mean exactly the same thing. Summed up together, we should find a total magnitude of 44.7 meters per second. Now the angle theta, I need to be a little bit careful with here, because I have called this from the positive y-axis on my picture rather than being from the x-axis. So for theta here, when I take my inverse tangent, I still need to do opposite over adjacent. But now, opposite is v of x. Adjacent is v of y. And then again, I take away the agency of the calculator. I make the answer positive because my picture tells me what direction these things are going. When I do that, I come out with an angle of 26.6 degrees. Call it counterclockwise from positive y. If you use compass directions instead, 63.4 degrees north from west, that would work. If you had said instead, well, I like this better as 116.6 degrees from positive x, I'd take that too. The most important part is that we can all agree. If we're saying different things, we have to agree that it means the same thing. No matter how I draw my picture, if you had drawn your picture instead with, let's do this in orange, let's say you had instead picked this angle phi from the negative x-axis, what would change? Well, I would see this, and I would see this, but we can all agree the sides are the same, the top and bottom are the same, right? We could agree that we could get back and forth between each other's pictures. We just need to do a little bit of conversion. No matter how you're describing these things, it should be all right. I could also say 26.6 degrees west of north if we wanted to do that instead. There's a lot of different ways to talk about these things, but again, as long as we can all come to the same conclusion at the end of the day, it doesn't matter how you describe it. As long as, the way you're describing it is correct. My very last one here. In purple, I'm given an acceleration vector, a, little a, 2 I hat minus 6 j hat. Meters per second squared. So, let's draw this thing out. A little bit of x, and then negative y, something like that, roughly speaking. Let's go back to just my positive from the positive x-axis. That's a common way to do this. I would get something like that. So my two components, I would have part of my x component going that way, part of my y component going this way. Oh, forgot to label. There's a vector, here's a hypotenuse, here's a of x, here's a of y. We've got a nice pretty picture. We go back to all of our classic things. A would be square root 2 squared plus 6 squared. Final answer of 6.32 meters per second squared. My angle, theta, and inverse tangent. I take away the agency of the calculator. I say I will determine what this angle is. This is opposite over adjacent. 6 over 2. I should get 71.6 degrees clockwise from positive x. Or if you want to call that negative 71.6 degrees, that's totally fine by me. So, we are not going to get through all these problems, which is probably not going to be a common thing, but it did happen last time, and unfortunately that kind of took away some of our time here, but that's all right. The last problem is not a hugely important one. One of the points that I do want to get to, though, to make sure that we can talk about this properly, is we just saw earlier how to graphically add or subtract vectors, and that's cool, but how many of my vectors did I draw accurately? Like, let's be real, right? None of them. All of my pictures are relative. They're close. They get the idea of what's going on, but none of them are exact. I'm not an artist, right? And even if I was, I probably wouldn't be a good one. So when I'm looking at these things, when we have these things given in component form, or when we're trying to get exact answers, and graphing these things out meticulously by hand is not an option, the better way to do these is to do vector addition through components. And all this is saying is that it is equivalent to take two vectors, to break them into components, and to add those components as it is to just add the vectors themselves. It does exactly the same thing, no difference whatsoever, right? Because we remember A can be recreated by combining AX and AY. So if we add A and we add B, then we're essentially adding AX, AY, BX, BY. all four of those together, that's what we have right here. So this is probably the best way to do a lot of this addition. You can't just add the total lengths of the vectors and then call it a day. You have to add the components of the vectors to get an accurate representation of your result. So if you wanted C, I need to combine the two x components, two y components. If I wanted to subtract, same deal, x's and y's. Just slap them together. So let's get a little bit of practice with this concept, and this is going to be our last one here. Let's say that we have a vector A and a vector B, and we are going to come up with some brand new vector f that is equal to A minus 4 times B. So that's A minus B minus B minus B minus B. Find the vector in component form. Draw out all three vectors. Find the magnitude and direction of vector f. Take the next 5 or so minutes to do this one, and then we will look at it all together. Okay, and I think it's probably a good time. Let's go ahead and take a look at this one together, and we'll finish this thing out. We won't go to Westeros today. You know, you can run through this one if you would like. It's mostly moving around some different vectors and everything else, though. Good practice, but not a huge deal that we don't get to it. So what we're going to do here is we are going to start by actually solving this thing out in component form. So we are given the vectors A is 4i hat minus 2j hat. We are given B as negative 3i hat plus 5j hat. We are told we are going to make F as A minus 4 times B. And this is kind of a fun thing because vectors have some cool different functions that you can do with them. The way that math works with vectors does not work the same as with regular numbers. So this is what's called scalar multiplication, where you can just multiply the vector by some number, and each component of that is going to get multiplied. Because what this is really saying is A minus B minus B minus B minus B. So with that many minuses, we might as well just take each quantity, each component, multiply it by 4, and then do the subtraction. So what I can do is I can break this apart, and I can say, well then f of x is really the x component of A minus 4 times the x component of B, or positive 16. I can do the same thing for f of y. I would say f of y would be the y component of A minus 4 times the y component of B. Negative 22. That means that the vector f in component form would be 16i hat minus 22j hat. Perfect. Excellent start. That is part A out of the way. Now we are going to draw these things so we can compare and contrast. And again, these are not going to be exact. I'm going to draw these as relative as I can get them without spending any real amount of time. So I'm going to take A plus 4 minus 2 is what we're looking at here. Plus 4 minus 2, kind of like this. Arrow, label it. B, minus 3 plus 5. Something like this, probably. Right around there. Give or take a little bit. Perfect. F should be much longer than the both of them, right? It's some big numbers right there. So 16i minus 22j, probably longer than this, but this gets us good enough for now. Something like that. So that's roughly what we could imagine this thing looking like. Now the last thing that I'm going to need to do is I'm going to need to find the direction and magnitude of this. So I could take this, I could take this. Those are my two components. This is f of x, this is f of y, this is the total angle f, this is my angle theta. Now, I'm going to say that the magnitude f is the square root of 16 squared plus 22 squared for a grand total of 27.2. My angle theta, again, Do not give your calculator the time of day as it comes to positives and negatives. It will not know how to handle them properly. It's just untrustworthy, is really what it comes down to. A lot of the time it might be right, but some of the time it's going to be wrong. And if you don't keep track of those things and you're not sure when it's supposed to be over here, down here, then you're just going to run into issues. But anyways, my angle theta, opposite over adjacent, that is 22/16. To give me 53.97 degrees. 53.97 degrees, and I'm going to call that clockwise from positive x. You could even say, if you wanted to, if you draw out the picture like this, you could always just say theta is equal to 53.97 as on picture. That would work just as well. And then if we need to break that up, we can look at the picture and figure it out ourselves. However you would like to do those things. I will take anything as long as we can all agree that it's going, at the end of the day, in the same direction. But if you need to get out of here, that's all I've got for the rest of the day.